All right, hello. Time to go over 6.1a, which is all about inverse functions, right? We have a new way of writing inverse functions, not reciprocal. Okay, there's a difference between reciprocal and inverse. So just really quickly before we jump into this, I'm sorry, my paper's kind of curled up here at the top. Remember that an inverse function, I go ahead and say it undoes what the original function does. Okay, an inverse function undoes what the original function does. So if I have something like, let's say I have y is equal to 2x minus 3. Okay, so this function takes an input, it multiplies it by 2, and then it subtracts 3 from that, right? So if I wanted to undo what this function does, the first thing I would do is move that 3 to the other side, right? And when I move the 3 to the other side, I would do that by adding, correct? Well, that's because addition and subtraction are inverses, because they undo one another, right? So then I would have y plus 3 is equal to 2x, right? And then I could get rid of the 2 by dividing off the 2, right? And that's because multiplication and division are inverses, or in other words, they undo one another, okay? So addition and subtraction and multiplication and division we've dealt with, like in college algebra, and talking about inverting those types of functions. And remember, the first thing we do is we make sure it's a function, and then we check to see if it's invertible, because not all functions are invertible, right? So first thing is the vertical line test. We all remember the vertical line test. Vertical line test says if we draw a vertical line anywhere on this, as long as it hits only one time, right? If I draw a vertical line here, it's only going to hit one time. That means that this is a function, okay? Same thing on this one. If I draw a vertical line anywhere on here, it's only going to hit one time, right? This is x cubed. This is x squared, right? These are functions we should be familiar with. This one's also going to be a function. However, my sideways parabola here, hold on, let me see if I can get rid of this. There we go. Okay, my sideways parabola here, if I draw a vertical line somewhere on it, right, it's going to hit more than one time. So if it hits more than one time, then that means it's not a function. Okay, and then this one, same thing. This is actually my cube root function. And notice if I draw a vertical line anywhere on here, it's only going to hit one place. So this one's also a function. So I think y'all probably are familiar with the vertical line test and checking to see if something is a function or not. What I want to review you on here for just a minute is the horizontal line test. So I don't know if you remember the horizontal line test. The horizontal line test checks to make sure that none of our output values are repeated, because when we do inverses, remember we swap all of our x's and our y's. That's how we do inverses, because if the original function said, okay, I'm going to take 0 and I'm going to add 3 to it, right, then 0 would get mapped to 3. So then the inverse function would take 3 and it would map it back to 0, right? Or in other words, our input and our output get swapped. So in order for it to have an inverse function, once we swap those variables, then our inverse also has to pass the horizontal or the vertical line test. So a way to check before we do all this swapping is we can just check the horizontal line test, right? So if I check a horizontal line test, and the 2 down here at the bottom are the exact same 2 as the 2 here at the top. So I'm just going to write it up here at the top. If I check a horizontal line test on this one, right, this one's going to fail because it's going to hit in 2 places, right? So what that means is that we cannot invert this function, because right now we have 2 x's that have the same y output, right? Which is fine for it to be a regular function, but when we invert it, that means that we would have one x that would be mapping to two y values, right? So that's, we can't reverse this process in a unique way, right? So no inverse function as it's written, right? Now, if we could only consider like maybe one side of the parabola, then notice just that one side would have an inverse if I restrict the domain, right? But if I take the entire function, it's not going to pass the horizontal line test, okay? Notice on this one, though, if I drew a horizontal line anywhere on here, right? Let's say I chose this value. Notice we only have one y value, right, for that specific x. So what that means is that this one is uniquely reversible because I can take the input, map it to an output. I can take that output and map it uniquely back to that same input, right? So this one would have an inverse. Okay? So when we're looking at these, and we're checking the horizontal lines test, is we're looking to see if it's uniquely reversible or if it has an inverse. Now, we write this a lot of different ways. So if you see these different words, they all kind of mean the same thing. So if we have a parabola like this, right, and we draw a horizontal line, we know it's going to fail, right? So we may say that there is no inverse function, okay? It's not invertible. Or we may say that it's not 1-to-1, okay? We went over this in college algebra. 1-to-1 means that every x gets mapped to one exact unique y value, and each y value is mapped back to one unique x value, right? We were talking about that being our monogamous function relationship, right? So a 1-to-1 function means every x goes to one y, that y goes exactly back to that one x. So here, it's not, right? This is a polygamous function, right? So this one's not 1-to-1. You might also see something like no inverse exists, okay? Or you may see something that says it's not a reversible function, okay? And I'm just writing all these down so that if you see this verbiage in your homework, that you'll realize it all means the same thing. It's just being expressed in a different way. Okay, or depending on what background you came in from math, if you didn't come from my specific college algebra class, you may have learned it as 1-to-1 or not reversible, or any combination of these. Okay, now if it does have an inverse, right, like our x cubed function here, we know that if we draw any horizontal line, it's only going to hit one time. So we know this one does have an inverse. Does have an inverse function, okay? Or you might see something like inverse exists, right? Or you may see the verbiage, it is invertible, okay? Or you may see it is a 1-to-1 function, okay? So any of these ways of expressing it, I want you to be familiar with, okay? All right, so let's go ahead and look at inverting or finding the inverse of a function. And I'm just going to refresh oh my gosh, my paper's not working with me. I'm going to refresh on maybe something you've seen before, and then I'm going to demonstrate how we're going to use this on our trig functions, okay? So let's look at this one. We know this is invertible. This is our x cubed function from the last page, right? And here we have a list of ordered pairs, right? So if I take -2 and I cube it, I get -8. If I do -1 and I cube it, I get -1. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So these are the points that are graphed on here to show you the shape of this function, right? So if we want to invert it, okay, what we're going to do is we're going to swap all of our input and output values, or swap our ordered pairs. So that would give us -8, -2, -1, -1, 0, 0, 1, 1, 8, 2, right? If we swap all of our input and output values. So I'm going to go ahead and graph these so that we can see what they look like. So over here at -8, we'd be down at -2. -1, we'd be at -1. 0, we'd be at 0. 1, we'd be up at 1. And 8, we'd be up at +2. So notice if I combine these, or not combine these, connect these rather, with my line, notice I'm getting the exact same shape. It's just kind of been rotated, kind of like flipped and turned to the side, right? So what this is giving me is this is actually giving me the function, which is the cube root of x, right? Because what undoes a cube is to take the cube root. In other words, if I cube -2, I get -8. If I take the cube root of -8, it sends me back to -2, right? So one way that we could write this is we could say that f of x equal to x cubed and g of x equal to the cube root of x are inverses, right? We could say those two are inverses. If I just give this one a name and give this one a name, right? Another way we could write this is we could say that if f of x is equal to x cubed, then f inverse of x, remember this notation that stands for the inverse function, then the inverse would be the cube root of x. Okay, so basically what we're doing, if you notice here, we have the same shape. It just looks like it's been turned. And what actually has happened is it is a reflection over this line y equals x. Okay, so inverses are reflections of the original function over the line y equals x. So if I were to take this black function, my original function, and I were to flip it across this blue dotted line that I just drew, notice this piece right here, when I flip it over across the blue dotted line, becomes this pink piece, right? The same thing with these little squiggles, right? They get inverted. Same thing on this side, they get inverted. And then the same thing with this nice long black piece. When I flip it across this dotted line, instead of being down here, it goes over here. So what we can do is we can model this by simply flipping and turning our page. Okay, so let me show you. I'm going to do this exact same one, but I'm going to show you how we're going to do it with the trig functions moving forward. So if you look at the next page, this has the exact same function on it, right? Where this is my y-axis and this is my x-axis, right? So what I want to do is I'm just going to like really boldly write, or color really, on top of this function. So it kind of bleeds through to the other side of my paper. So if you didn't print yours front back, that's okay. Because if you'll notice in your notes, the back side of this page should be blank. All right. All right. So if I deeply bold this function, and then I turn my paper. Now I want you to pay attention to the way I'm going to turn it. I'm going to grab it up here at the left side corner, and I'm going to turn it this way. Okay, so turning it this way, notice you can see where I've bolded and written it. Now when I turned it, my y used to be up on the top, right? My y-axis was my vertical axis, and my horizontal was my x, right? And I can even see here where I had written the y-axis, and then this was the x-axis. So when I invert, remember my y's become my x's become my y's. So even though you can see through my paper that this used to be labeled as an x, this now is going to become my y-axis, right? And even though you can see this one was labeled as my y-axis on the other side, it is now my x-axis. And just by simply rotating it, right, again, I'm going to show you how I did it. So if we take our original function, we're going to grab the top left corner and we're just going to pull it down, right? That's how I'm going to flip my paper over. That inverts our function for us because it flips it over the y equals x line. And you can compare this with the one we did on the last page, but you can see here, this is the graph of the cube root of x, right? So that's a neat way to be able to invert your function, is just to trace it on one side of the page and then turn and reflect it, right, on the back side, relabel your x and y axis, and that gives you your inverted function. Okay, so I want to do this with all of the trig functions so we can see what their inverse functions look like. Okay, all right, so let's go back over here. If you'll notice at the bottom of page 3, there's this little chart here, and this is just kind of more of a FYI for your information, just like some notation. So just like we're used to saying two functions are inverses, and we are used to this little sign to the -1 power, meaning that that's the inverse of sine. You'll see both of these, but this is just kind of a new notation, all of this arc sine stuff. Okay, the arc means the same thing as the little -1 exponent. Okay, it's just a notation that means inverse function. Okay, so if you see sine to the -1 power, you know that's the inverse of sine. Or if you see arc sine, that also means the inverse of sine. Okay, so I want you to be familiar with these two notations, meaning that that just means it's the inverse of sine. Okay, all right, so let's go ahead and look at the functions that we're dealing with. Now notice here, because sine and cosine and, well, really all of our trig functions repeat, right? Our sine curve goes on and on and on and on. Our cosine curve goes on and on and on. Our tangent curve, we can just keep drawing it and drawing it and drawing it, right? So when we invert this, we kind of come up with the same problem we did on some of our parent polynomial functions and things like that we've dealt with. Is if I were to draw a line, like check this with the horizontal line test, it's actually going to fail, right? Because I have repeating y values, and I don't want repeating y values because that creates an uninvertible function, right? So what I'm going to do is I'm going to restrict my domain, meaning the piece of this function that I choose. I want to choose a piece where if I did the horizontal line test here, notice everything between my fingers, there's no repeating y values, right? Or if I chose to do it from here to here, there's no repeating y values, okay? So I'm going to restrict my domain so that I don't have those issues with not passing the horizontal line test, okay? So let's just write up here our goal. Okay, so the first thing is we want to make sure that we include all y values, that our graph, however we draw it, hits every y value it's supposed to hit. Meaning, our sine curve starts at 0, right? And then it goes up to 1, back down to 0, down to -1, and back up to 0, right? So our sine curve should cover every y value between -1 and 1, right? Somewhere within that curve, it should hit all those y values. So that's our first goal, is we want to make sure that we hit all the y values. Okay, so if we restrict our domain too much, we may not hit the higher ones, or we may not hit the lower ones. We want to make sure we hit all of them. The second thing we want to do is, even though we want to hit all of them, we don't want to hit the y values more than once, right? We don't want repetitive. So let's say we don't want any repetition. Want any repetition. Okay. And then the third thing is we really want 0 included, okay? Want 0 included. And maybe I shouldn't say included because sometimes functions have an asymptote at 0, right? So let's just say graphed, okay? Whatever's happening at 0. The reason that we really want our function to include 0, or that area on our graph where 0 is because if we're going to take our y-axis and we're going to turn and rotate it so that we can flip it and find the inverse, it's nice to have that reference point of where our x and y axis cross, so that whenever we invert it, it's really easy to see our inverse function. Okay, now we could choose different areas of our function and still be able to graph an accurate depiction of the inverse, but we want to try to get it included around 0 so that it's easier for us to graph. Okay, so let's go ahead and look at this function. If I look at this first function, this is our sine function, and we know that sine goes from what we normally do to get all the way around the unit circle is we start at 0, right? We start at 0, we go up to 1, we come back down to 0, and then we go to 2 pi, right? Now, that is repeating values, right? Because notice here, I hit 0 here, but I'm also hitting 0 here and 0 here. So this is not the best way to draw it so that we include all of the sine values. Okay, I do need to make sure I have all the values from 0 up to 1, but then I don't need to include all those values again from 1 down to 0, right? So this little piece, I'm going to use a different color so that you can see. This little piece will give me all of the values from 0 up to 1. And now really the only other pieces that I'm missing, because this goes from 0 up to 1, I need some representation from 0 down to -1. But I don't want to skip over and do this because then I have a weird gap. So I'm looking for another piece on my picture where I can go from 0 down to -1. And what I can do is instead, I can just go in this negative direction, right? If I use this piece of my sine curve, notice I am covering all the y values because from -1 all the way up to 1 is covered, right? Which is my range. And all I'm having to do is restrict my domain from -pi/2 to +pi/2. And that allows me to get all of those y values that I need in there. And notice it also includes 0. So that's good. So I'm going to go ahead and just put on here, I'm going to restrict my domain from -pi/2 to pi/2. And I'm including those values, so I'm going to use brackets, right? And I'm doing that so that we end up with all the y values we need, which is from -1 to 1. Okay. Oh, excuse me. Okay, so this is my sine function, right? F of x equals sine x. I know it's written here, but it's really teeny tiny and small. Okay, so what I want to do is I want to invert this so that I can figure out what the arc sine function is, or the sine inverse function. So just like before, right now this is my y-axis, this is my x-axis. I want to do the same thing I did before, grab the left-hand corner of my paper and pull it down, right, so that I can flip this over. And now you can easily see here, hopefully yours is looking better than mine. I'm going to go ahead and trace this over. Try to get it up there. So you can see we restricted our x-axis from -pi/2 to pi/2. So when I invert that, that's actually my y-axis, right? So now on my y-axis, I'm going from pi/2 to -pi/2. pi/2, -pi/2, right? When I invert it. So now that it's inverted, it looks like this. I can see through where I went over it, so it looks like that. Okay, so this is my arc sine, or my sine inverse function. Sine inverse of x. I'm going to put parentheses around it because it's just habit for me. Okay. And then I'm also going to now list what the domain and range is of this new inverse function. And it shouldn't be hard to figure out, right? Because the domain is the range of my original, and my range should be the domain of my original, right? Because all I did was swap all my x's and y's, which basically means that I swap my domain and range. So you can see here that this is going to go from, let me label this. This is from -1 to 1, right, on my domain. And then my range is going to go from -pi/2 up to pi/2. Okay. So again, if you need to pause it, go slower, feel free to do that, but I'm going to go ahead and go back over what I did. So I took my original function and I determined where do I need to trace this? You know, what piece of this function can I use so that it covers every single value from -1 up to 1, and it includes 0, and I'm not repeating y values. So that would be this little piece, right, from here up to here. And so I wrote out what domain values cover this little piece. So this little piece goes from -pi/2 over to pi/2, right? And my y values go from -1 up to +1. So now that I have that, again, grab the left-hand side of my paper and invert it down. And then all we have to do is relabel. So we can see our function here. But this time, instead of our x's going from -pi/2 to pi/2, our y's are going to go from -pi/2 to pi/2. And instead of our y's going from -1 to 1, now it's our x's that are going from -1 to 1. Okay? So that's what we want to do for the rest of these functions. So let's try again with cosine. So looking at our cosine value, cosine, we want to cover everything, right? Cosine, normally we start up at 1 and we do this whole curve, right? Now we don't need the whole curve, we just need the curves that cover all of our range values. So just like sine, our cosine values go from -1 up to 1. So I do want to include 0, but I don't want to include this hump because this whole hump is just covering from 0 up to 1. So I'm going to start where we normally do up here at 1, and I'm going to trace just until I have all the values from 1 down to -1. So this gives me all the values from 1 down to 0, right? And then this gives me all the way down to -1. Okay? So this is really the only piece that I need, because you can see I've covered from -1 up to 1. That's the range that I wanted. And all I need to do is restrict my domain, because normally our domain goes on and on and on and on and on, right? But we're going to restrict our domain so that we're not getting repeating y values. So our domain here is going to start at 0, and then it's going to end right here at pi. And we want to include those values so we actually get -1 to 1, right? So make sure you use brackets. And then our range here is going to be -1 to 1. Okay. So now that I have that graphed, this was my y and this is my x, right? So when I flip it over, those should be opposites. Okay. So again, grab the left corner, and we're going to flip our paper so that it's rotated. And you can see it appears right up here above my sine function. So you can see through my paper, hopefully, a little bit where I had labeled this x and this one y. But now this is going to be my y-axis, and this is going to be my x-axis, right? So we can see the paper through. And I think trying to see the line. I may have to start going over the axes with my darker pen so it transfers over also. All right, so this is going to be my inverse function for cosine inverse of x. Okay, so let's go ahead and graph it. Looks something like this, right? Now remember, our original over here, if I flip it back over, the domain went from 0 to pi. So our x's went from 0 to pi. So now our y's, when we flip it over, are going to go from 0 up to pi. Okay? And our x's, right, our side-to-side values from here to here, I need to look, okay, our original, our y values went from -1 up to +1. So now those range values are going to become our domain values, our x values. So it's going to go from -1 to 1. Okay, so I'm going to go ahead and list my domain and range here. So my domain is -1 to 1, and my range values are from 0 to pi. Okay, are we kind of okay with this process? All right, so let's look at the next one. All right, so if we look at our tangent, okay, the first thing I want to look at is I want to think about what values does tangent cover, okay? Remember with sine and cosine, one full sine or cosine curve goes from -1 up to 1. But tangent, remember, it's unbounded. It can keep going and going and going, right? So when we think about our tangent curve and needing to cover all y values, right? Notice here it keeps going. I don't have y values that are repeating until I go to the next cycle of tangent, right? So on this one, I can actually take the whole entire thing, right? Because none of those y values are ever going to repeat. These are going to keep giving me bigger y values. These are going to keep giving me smaller y values. And I just have to make sure I don't repeat any cycles, okay? So I want to take this, but I also want to make sure that I include my asymptotes here, okay? Because that is very important that I include those asymptotes, okay? So I'm going to go ahead and write down here that my restricted domain is going to be from asymptote to asymptote, right? So -pi/2 to pi/2. So I actually get a full cycle of tangent, right? And then our range values are -infinity to infinity, right? Because it just keeps going and going. We don't have to restrict it. All right, and then I'm going to go ahead and I'm just going to go and copy over my x and y axis so that it transfers over a little bit. Okay. All right, so again, I'm going to grab the top left-hand side of my paper and flip it. And you can see here that I now have my inverse tangent function right next to my sine function. And that did help going over my x and y axis. So I'm going to go ahead and draw my x and y axis. You can see here this used to be my x-axis. This is now my y-axis. This used to be my y-axis, which is now my x-axis. And we're going to go ahead and put in our function. So now it looks something like this. And our asymptote. And let's see if we can fill in the domain and range without flipping it back over to the other side. Okay, we were using our tangent function, so we know this is an inverse tangent function. Now remember, this doesn't mean it's cotangent. We're not talking reciprocals. We're talking inverse, okay? So remember that -1 does not mean to invert it. I mean to do the reciprocal. It means we're doing the inverse function, okay? So tangent normally goes from asymptote to asymptote, right? That was our domain. So our domain now becomes our range, right? So asymptote to asymptote. So this point right here would be -pi/2 up to a +pi/2, right? So our range is now restricted between -pi/2, whoops, and I need to be using parentheses. I need to make sure I did that on the other side, right? Because these are asymptotes, so we can't touch them or cross them, so they're not included. So we should have parentheses here. Sorry about that. Okay. And then our domain for this function is how far left and right it could go, right? And remember, tangent, when we drew this on the other side, it just keeps going and going and going up and down, right? Without bound on y values. So when we invert that, now left to right, we're going to be able to go without bounds. So negative infinity to infinity. Okay? Does that kind of make sense? All right, I'm going to go back over on the other page now and make sure that my original domain I used parentheses on for those asymptotes, because I don't think I did. So if I flip this back over, nope, I did not. Bad, Miss Williams. So these should be parentheses, okay? All right, so I'm going to go ahead and move down now. I'm going to skip this one because I'm going to have you try these two here in a second, okay? All right, so let's look at cosecant. So cosecant here, I need to make sure that I include all values. Now notice cosecant starts at 1 and it shoots up to higher values, right? Or it starts at -1 and shoots down to lower values. So I need to make sure that I have this point included at 1 and -1, and then that I have that representation of it going up from 1, right? And a representation of it going down from -1. And I really want to try to include 0 if I can. So when I pick the pieces I'm going to use, I want to use the ones that are going towards 0. So I'm going to use this piece right here, and I'm going to use this piece right here, right? Because now I have all the y values from 1 up, and I have all the y values from 1 down, okay? And then I want to go ahead, remember this is an asymptote, it happens to be our y-axis, but it is an asymptote, so make sure that's included. And then we need our x-axis. Here's our x, and I can't draw, I guess here's my y. Okay, so I need to think about what does that look like for my restricted domain, and what does that look like for my range, okay? So as far as my restricted domain, from left to right, how far am I going? Well, the first piece that I used was right here down, right? And notice this piece starts at -π/2, and it's included, right? It's not an asymptote. So I'm going to start at -π/2, and it's going to go all the way over. Now I can't go from here all the way over to this π/2 because remember the y-axis is an asymptote, which means it can't touch or cross. So I'm going to go from π/2 over to 0 where my asymptote is. I have to take out the asymptote, right? And then I can do this piece, which goes from 0 on over to π/2, right? π/2. And then I need to list my range values. My range values, notice we start at the lowest. Well, this is going to shoot down to -infinity, right? This piece is just going to keep going lower and lower and lower and lower. So -infinity up to where this piece ends, which is right here at -1, which is included, right? And then I don't have any y values from -1 to 1, but it does pick up again at 1, right? And then from 1, then it's going to shoot on up to infinity on our y-axis, okay? All right, so there's our domain restriction, -π/2 to π/2 minus the asymptote in the middle, right? And then our range is everything from -1 down and everything from 1 up, okay? So now let's go ahead and flip our page over and see what this looks like. So again, I'm going to grab the top left-hand corner and flip it on over, which it should be down here next to our tangent function. All right, and hopefully I can see it well enough to trace it. So here's our axis, right? You can see here this used to be my x. Now this is going to be my y, and this is going to be my x. And you can see I have the little tick marks listed here, okay? So let's go ahead and draw in our picture. Something like this. Okay. All right. And remember, the y-axis was an asymptote. So when I invert this, now my x-axis is an asymptote. So I'm going to go ahead and just draw that on top of the x-axis so that we can see it there. Okay. So remember, this was our cosecant function. So what we just found is our cosecant inverse function, right? So I want to go ahead and list my domain and my range. Okay. So remember, our domain originally started from negative pi over 2 to pi over 2, and we took out that asymptote in the middle, right? That was my domain. So now that's going to be my range. I'm going from negative pi over 2 up to pi over 2, right? Minus this asymptote in the middle. So negative pi over 2 to 0. Take out the asymptote in the middle, and then we go from 0 up to pi over 2. Okay. And then we do the same thing with our, oh, I just wrote it on the wrong thing, didn't I? I sure did. Silly me. That's our range. That was our original domain. So when we flip it, now that's our range. Let me write it right here, and then I'll take it off. Sorry. Sorry if that confused you because I wrote it in the wrong spot. All right. Meow. 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 Okay. So remember, when we had this flipped on the original page, we had the piece that started at 1 and went up, and we had the piece that started at -1 and went down, right? Those were our range values. The piece that kept going up and the piece that kept going down with nothing from -1 to 1, right? So now that we've flipped and inverted it, now that's going to be our domain. So notice it goes from -infinity up to this point, which is -1. So -infinity to -1. And then over here, it's going to start at +1 and shoot on out to infinity. Okay. And if you have to, you're welcome to flip your paper back and forth just to verify what I'm saying and what I'm doing. But it gets really nasty on a video when I keep flipping it. Students get annoyed by the flipping of the paper. Okay, so here's what I want y'all to try. I want y'all to try these two that we didn't do. Okay, so I want you to try the cotangent and the secant. So I want you to come up with which piece do we need to invert so that all of our y values are covered, so that none of our y values are repeated, and so that 0 is included or at least graphed on our inverse function. Okay, so go ahead and pause the video and give those two a try, and whenever you're ready or if you get stuck, play the video and I'll go ahead. All right, so let's see how you did. So looking at the cotangent one, we need to take the entire function, right? None of the y values get repeated, so we can take the whole thing, and our restricted domain in order to get this whole picture is going to be from 0 out to pi. Okay, now remember there's an asymptote here at 0 and there's an asymptote at pi. So make sure you're using parentheses to represent that domain because we cannot include those endpoints. Okay, and then our range is going to be from -infinity to infinity. So I would go ahead and trace over the x and y axis. Make sure you write in your asymptote. And then when you take the left-hand corner of your paper and flip it over, oops, and I didn't even write what the function was over here. We should end up with this. So now instead of our y's going from -infinity to infinity, notice now our domain or our x's are going from -infinity to infinity. And instead of our x's going from 0 over to pi, now our y's or our range are going to go from 0 up to pi. So instead of those vertical asymptotes, we now have horizontal asymptotes, and this gives us our y equals cotangent inverse function. Okay. If you need to spend more time on it, go ahead and pause the video, but I'm going to go ahead and move on to the next one. All right, so the next one I had y'all do was the secant function. So secant function, it could go different ways depending on what you chose. Now, I always choose to go in the positive direction when possible. So the secant I need from 1 up to infinity, and I also need from -1 down. So notice I didn't use this side because that would have put me down into negative x values. So I'm going to use the right-hand side. I'm going to use just this piece of that top parabola and then just this side of the next parabola. So domain-wise, I'm starting at 0, which is not an asymptote here, right? So 0 can be included with a bracket. And I'm going all the way over to pi, which is also included with a bracket. However, I have an asymptote in the middle at pi over 2. So I do need to take that out with parentheses, okay? So domain is from 0 to pi included minus the asymptote in the middle that we have to take out with parentheses. Okay, and then as far as my range values, I start with my lower one. This is going to be from -infinity up to -1, and then this piece will go from 1 up to infinity. Okay, our 1s are included and our infinities have parentheses. So whenever I flip this over, again, grab that left-hand corner of your paper and flip it over, we should end up with y is equal to secant inverse of x, looking something like this. Okay, so this time, instead of our domain going from 0 to pi with an asymptote in the middle, right, that's been reflected over onto the side. So now our y values are going from 0 up to pi with an asymptote cutting through the middle. Okay, so again, you can always just take your domain and range from the other side of the paper and swap them. Right? Make sure you label your paper though, because these reference points are going to come in very, very handy when we start doing our calculations on the next page. Okay. And then, what else was I going to say? Yeah. And make sure you draw in your asymptote. Okay. All right, so these are all of our inverse functions. So now on this one page front and back, you have a graph of all of our 6 trig functions. And now on the back side, you have all 6 inverse trig functions, okay? So here's where we're going to go from here. I did give you a chart on page 7. So this is kind of an extension of the chart I'd given you before. So not only is it the degree measures, but it's also the radian measures. So this is basically our x, right? So whatever x we're plugging in, we're going to get out a y, right? Which here we have sine, cosine, tangent, cotangent, secant, and cosecant. So all 6 trig functions basically means here we're going to, this is the sine x value. This is the cosine x value, right? This is the tan x value, cotangent of x, secant x, and cosecant x. So just for your reference, and we will use this page here in a minute when we start calculating. So let's go ahead and see now that we have these values, how we're going to use them, okay? All right. So page 8, we have our circle here. Okay, now I have this circle so that we can reference it, but remember a lot of these functions, and I'm just going to put this back on here, this is page 6. A lot of these functions, we now know the domain of them, right? We know the specific, they go from this to this, they go from this to this. So we want to keep that in mind when we're looking for our values on the unit circle, okay? So for example, okay, we want to find y, okay? So this one is talking about arc sine. So the arc sine of this x value, right? We're looking for the corresponding y. So first what we want to do is we want to make sure, if we know we're looking for the sine value, right? The arc sine, let's look back at our picture here for our sine inverse. Okay, so this is also our arc sine. So these are the graphs we just did. and we're looking for the y value, okay? So the y value, notice, has to be between negative pi over 2 to pi over 2, okay? So if we can't find an answer within that, then we have no solution, okay? So negative pi over 2 to pi over 2. So I'm going to go ahead and just write that down. Trying to find the angle with the given sine value. Okay, obviously all of these are dealing with sine, and we know that negative pi over 2 to pi over 2 is our range, right? And this is because the domain was restricted. Okay, it's because the domain was restricted. So if we're looking for y values, they go from negative pi over 2 to pi over 2. Let's think about what quadrant that's in. Okay, we're looking for possible angles. So I'm just going to draw a little picture over here to the side. So if I have my unit circle, right, if you will, this is where negative pi over 2 is, and this is where positive pi over 2 is. So any of the angles that fall in quadrant 1 or 4, these are the possible angles that we're looking for, okay? Possible angles. So if I look at this, I want to go ahead and just figure out what my sine value is, because then it'll be really easy to look on my chart and find that, because we don't really have a chart for arc sine, right? We could use the chart on the other page, but I want to show you how to do it with a unit circle because that's what we're familiar with. So if I want to get rid of arc sine, remember arc sine is the inverse of sine. So if I want to undo an inverse, I just use the original function. In other words, I can take sine of both sides so that sine and arc sine will cancel. But if I do that on one side, I have to do it on the other side, right? So here, sine and arc sine are inverse functions, so those will cancel. So basically what I'm looking for is I am looking for an angle whose sine value ends up being square root of 3 over 2. Okay, so I'm going to look up here at my chart and see where do I have angle values where the y is square root of 3 over 2. So if I go up here, I'm looking at the y's. Here's a square root of 3 over 2, right? And here's a square root of 3 over 2. And down here, all my signs are negative. So I have two possible answers, right? But remember, arc sine has to fall with angles over here with values between negative pi over 2 to positive pi over 2. So this is the one that I want to take, right? So I'm looking for which angle did this satisfy. So if I look here, that's the angle of 60 degrees, right? Or pi over 3. So that means that y had to have been pi over 3. And that's my solution. Okay, so if you're doing this on your calculator and you're applying sine to sine inverse, it will only give you one answer because it's already set up with these restrictions. Okay, but when you're working it out, make sure you think about the quadrant or the possible angles, the quadrants they could come from because of the domain restrictions that we had in making sure that it was an invertible function. Okay. All right. So let's look at the next one. This one says sine inverse of -1/2 equals y. So again, this is the same as the last one. It's just written with a different notation. So arc sine is the same thing as sine inverse. So to get rid of sine inverse, we can just apply the regular sine function. So we're going to do sine evaluated at sine inverse of -1/2. is equal to sine y. Again, sine and sine inverse are going to cancel out. So we have a -1/2, which is the sine value we're looking for to determine what this angle y is. Okay, so we're looking for a -1/2 for a sine value. So let's go back up here and look for a -1/2. So I'm going to use a different color just because we're on a different problem. All right, so -1/2 is a sign value. Well, sign values we know are corresponding to the y values, right? So in these two quadrants, all of our sign values are going to be positive. So a -1/2 sign value is going to be down here in these two quadrants. So notice I have a -1/2 sign value there, and I also have a -1/2 sign value here. Okay, but again, we restricted that domain, right? So we're only looking at angles in quadrant 2 or 4. So this one has to be my answer, okay? But notice here, it's listed as 11 pi over 6, right? We're saying that y has to be 11 pi over 6. Well, if you look back at our arc sine, we didn't graph it all the way out to 11 pi over 6, right? We graphed it only from -pi over 2 to pi over 2. So what I'm going to do is, instead of representing this answer as 11 pi over 2, because I want it to fall within this range here, or within these possible angle measures, I'm going to express it as a negative angle, right? Because this is right here, right? So I could express an angle that's right here as a negative angle, like this is 0, right? And I could go up 2 pi, or I could go down to -pi over 2. So I want to think about going down in the negative direction. So if I go down, this is like subtracting, right? And since it's a 30-degree angle, it's like I'm going, because, right, if I go down to this first 30-degree line, it's the same as going up to this 30-degree line. So instead of going up to pi over 6, this is like going down -pi over 6, right? Or you could take 2 pi and subtract 11 pi over 6. However you want to figure that out. But this is going in the negative direction, pi over 6. So I'm going to mark this out. And I'm going to say we want the corresponding negative angle. So that means that y is equal to -pi over 6. Okay. All right. Let's look at another one. Add another one. All right. So this one, it says sine inverse of pi over 2 equals y. So again, to get rid of sine inverse, we're going to apply the sine function to both sides. So sine evaluated at sine inverse square root of 2 is equal to sine of y. So my sine and my sine inverse are going to cancel, and I have the square root of 2 is equal to sine y. Okay. Now notice if you look up at our unit circle at the top of the page, we're looking for a sine value of square root of 2. And if you look all the way around, I don't have a sine value of square root of 2, right? I don't have a full square root of anything. I have a bunch of fractions. So I'm going to double check something, because remember, our sine values have to be between -1 and 1, right? So I'm just going to figure out what the square root of 2, if I type that into my calculator, that comes out to 1.41 and some other stuff, right? So what this is saying is we're trying to find an angle whose sine value is 1.41 and some other stuff. And it's not possible, right? Because all sine values, if you think about that sine curve, regardless of what piece you chop at it, right, that sine curve is always between -1 and 1. And so this is actually not possible, right? I'm going to say sine values all between -1 and 1. So not possible. So I'm just going to say no solution. No solution here. Okay, so if you get something funky that you can't find the answer for, really think about, is this even something I could possibly get a solution for? Okay, all right, I have a couple more that I want to go over. And actually, I might have y'all try some. Let's look at the top of the next page. Oh, that's not the next page. This one's talking about arc cosine, okay? So if we look at arc cosine, if we're looking at the values that it can take on, let's look back at our graph. So we're looking for the y, right? We're looking for the y value of an arc cosine function. So that means that our range value of an arc cosine function is from 0 to pi. Okay, so it has to be something that falls between 0 and pi. So I'm going to go ahead and write that over here. Here's 0, here's pi, right? So some angle that falls within here, these are our possible angles for the solutions to these problems, because we're dealing with the arc cosine. We're looking for the y value, and we know the range of arc cosine falls between 0 and pi. Okay, so I'm going to go ahead and just write this. I think I wrote it already, but I'm going to write it like that. Okay, all right, so I want y'all to pause the video, and I want you to try to calculate these two answers and figure out what angles give you this arc cosine value. Okay, so pause it, try it on your own. If you get stuck or you need help or you're ready to get checked, then replay the video and we'll go over it. Okay, let's go ahead and see how you did on the first one. Remember, arc cosine is just the inverse. So to get rid of the inverse, we apply the regular cosine function to both sides. So that means we have 0 is equal to cosine y. So we're trying to figure out what angle, when we take the cosine of it, do we find 0. So you can look back at page 8 and use the unit circle, right? And we're looking for angles within this first quadrant. So if I look at angles within this first or second quadrant, and I'm looking for a cosine value of 0, okay? So cosine is our first, right? Because we have cosine, sine as our ordered pair. So we're looking for where cosine is 0. So if I look at all these ordered pairs, this is the point where cosine is 0, and you can see that that happens at pi over 2. Okay, so our angle is pi over 2. Okay, does that make sense? All right, and unless it tells you to use degrees, we just assume it always wants it in radians. Okay, all right, let's look at the second one. The second one is same thing. We take the cosine to get rid of the cosine inverse. If we do it on one side, we have to do it on the other. So we're looking for an angle whose cosine value is 1/2. So if I look at my unit circle again, remember I'm only considering angles within quadrant 1 or quadrant 2. So where do I find a cosine value of 1/2 is right here, and that's at pi over 3, right? Now notice I do have another cosine value at 1/2 down here, but because we're dealing with cosine, we can only have angles between 0 and pi. So we're looking for the angle that falls within one of these two quadrants, right, for our answer. We can't use the one down here. Okay, so it's always nice to be aware of where your possible solutions can come from. Okay. All right, let's move on. I want to do just a few more, and then you can get to your homework. All right, so this one, we're dealing with arc tangent, okay? Arc tangent. So again, let's bring back our little graphs that we came up with. If I look for arc tangent, notice its range values, right, are going to be between negative pi over 2 and pi over 2. Okay, those are our outputs between negative pi over 2 and positive pi over 2, not included. Okay, so I'm going to go ahead and just make myself a little note over here. Here's where negative pi over 2 is. Here's where positive pi over 2 is, right? So all of our possible angles have to be over here in either quadrant 1 or quadrant 4, okay, when we're dealing with tangent. So notice these are different based on every problem. These two were dealing with cosine, or sorry, arc cosine. So we knew our possible angles were from 0 to pi. And these are dealing with arc tangent or tangent inverse. So we know that our values have to be between negative pi over 2 and pi. Okay. All right. So let's go ahead and try to solve this. And then notice in these examples, this one specifically says to find our degree measure. So if we're looking for our degree measure, they want our answer in degrees, not in radian form. Okay. All right. So to get rid of arc tangent, we're going to take our regular tangent value. So tangent evaluated at arc tangent square root of 3 is equal to tangent theta. So our tangent and our arc tangent cancels out, and we have square root of 3 is equal to tangent theta. Now, tangent and cotangent are the reason that I gave you this graph. Okay, because if I were to try and look up on my little unit circle to find tangent values, I don't have them right on a unit circle. I get tangent by the ratio of sine to cosine, and I don't want to have to calculate that for every single thing to figure out where is my tangent square root of 3. So I'm going to use this chart. Okay, so I'm trying to figure out which angle has a tangent value of square root of 3. So when I look at this chart, I'm looking for the tangent value, which is this column, and I'm looking for square root of 3. So I'm going to come down here until I find a square root of 3, and there's one right there. And then let's see, there's one right there. So that's it. I have two possible answers. So I have 60 degrees has a tangent value of square root of 3, and 240 degrees has a tangent value of square root of 3. So I have to think about where those are. It's either 60 degrees or 240, or it could be both. So 60 degrees or, what did I say, 240 degrees, right? So remember, our possible angles have to fall within here. And because this goes from negative pi over 2 to pi over 2, this is the same thing as negative 90 degrees up to 90 degrees, right? So 60 falls within here, so that works, but 240 doesn't, right? 240 is over here in this quadrant over here, so that one doesn't work. So that means that theta has to be 60 degrees. Okay. All right, let's look at another one. This one is cosecant. So let's go back to our cosecant graph and see what its range is. So cosecant here has to be between negative pi over 2 and pi over 2, but there's an asymptote at 0. So basically the way we can write this easily is it has to be from negative pi over 2 to pi over 2. So that's very similar to what we just had for tangent, right? What I have written here for my possible angles, except this time it can't equal 0. Tangent could, but cosecant cannot equal 0, right? Because we had to take it out of our possible answers. So when we look at cosecant, cosecant has to be between negative 90 degrees and 90 degrees, right? And this cannot equal 0. Or in other words, right, our possible angles are over here. It cannot equal 0. 90 degrees to negative 90 degrees. Okay, however you want to write it so that you know what it means is fine with me. All right, so to get rid of cosecant, we need to use our regular cosecant inverse. We need to take cosecant of both sides. So cosecant evaluated at cosecant inverse square root of 2, negative square root of 2, is equal to cosecant theta. So our cosecant and cosecant inverse cancel. So I have negative square root of 2 is equal to cosecant theta. Now, here, normally what we would do is we would change this into sine so that we could then, look it up on our unit circle. But since we have this nice handy dandy chart available to us, I'm going to go ahead and just look up what angles have a cosecant value of negative square root of 2. And I'm going to use a different color. So on my chart, I'm looking for cosecant values, which is this last column, and I'm looking for negative square root of 2. So I have this one, which is at 225 degrees, and I have this one, which is at 315 degrees. So there's two angle measures that give me a cosecant value of negative square root of 2, and that's 225 degrees and 315 degrees. So it's either 225 degrees or it's 315 degrees. Okay, so I'm going to get rid of that, and then I'm going to reference this back. So if I look at 225, well, this would be like 180. That would be over here somewhere, right? So that's not within our allowable possible angles. So then I look at 315. 315 is going to be where? Somewhere in this quadrant, right? Because it's between 270 and 360. So this one is okay. That one works, right? So that means that our theta has to equal 315 degrees. Okay. And remember, we're only using degree measures here because it asked us to find the degree measure. Okay. If it just says find the measure of the angle, find the angle, we assume it's in radians. We only use degrees if they tell us to use degrees. Okay. All right. I have two more that I want to look at. Really, just this first one is the main one I want to look at because it's kind of tricky. So for this one, it says use a calculator to find theta in degrees, okay, if theta is equal to arc cotangent of negative 0.2528, okay, and it says be careful. So we're going to talk about why. So the first thing we want to do is we're looking for theta, and we're talking about arc cotangent. So I'm going to go ahead and go back to my little page here where we graphed all of them and look and see that arc cotangent, the range of it is anything from 0 to pi. Okay, so we have to figure out an angle that's between 0 and pi that gives us this value. Okay, so I'm going to go ahead and write here for our theta. Theta has to be between 0 degrees and, what did I say, pi? Yeah, 180, right? So 0 to pi. Okay, so it has to be between 0 and 180 degrees. So this is what I was given for my range on my graph just now, but I converted it to degrees since this one wants our answer in degrees. Okay, all right, so let's think about how I would solve for this. First thing is I want to get rid of arc cotangent because that's not something helpful that I can look up. So to get rid of arc cotangent, which is the inverse of cotangent, I want to go ahead and take the cotangent value of both sides. So that gives me cotangent theta is equal to cotangent arc cotangent of negative 0.2528. So my cotangent and my arc cotangent cancel, which means I have a cotangent theta that's equal to negative 0.2528. Now, this is not something I could do using that chart that we were just using, right? Because the charts gave us exact values of nice quadrantal and nice reference angles, right? This one obviously is coming out kind of wonky. So I want to be able to use my calculator. Now, in order to get this angle by itself so that I can punch it into the calculator, I would need to take the inverse of cotangent, but that would get me back here, right? And I don't have an inverse cotangent button on my calculator. So what I'm going to do is I'm going to change this into tangent because I have a tangent inverse button on my calculator. Okay, so that's why we gotta be careful. So we're going to talk about that in just a second. So let's go ahead and change this into tangent. So if I wanted to write this as tangent theta, right, we know that tangent and cotangent are inverses. So all I would have to do is invert this number. So I could write this as 1 over negative 0.2528, right? And now I can solve it for the theta. So to get rid of the tangent so that I can plug this into my calculator, right, I need to take the tangent inverse of both sides. So I'm going to do tangent inverse of tangent theta is equal to tangent inverse of 1 over negative 0.2528. Okay, so this side they cancel. And on the other side, tangent inverse, this is something I can plug into my calculator, right? Because wherever your tangent button is on your calculator, I'm going to show it with mine. Yours is probably very similar, unless you're using a graphing calculator. Shame on you. So wherever your tangent button is, you can see here, hold on, there's my tangent button. And right above it as the second function is tangent inverse, right? I know we've gone over this before. So we're going to go ahead and just type this into our calculator, and we should get negative 75.8 degrees. Okay, make sure your calculator is in degree mode. All right, so what we just figured out is we found the angle measure for tangent, okay? Now, our original problem started out with cotangent, not tangent. So let's think about this for just a second. When we look at tangent, tangent values, if we look back over here, let me find my page. Tangent values go between negative pi over 2 to pi over 2, right? We solved using inverse tangent. So tangent inverse output values are from negative pi over 2 to pi over 2. Are you with me? Okay, we use tangent inverse to solve. We know that the output values, if we look at our graph of tangent inverse, it goes from negative pi over 2 to pi over 2. Okay, so what that tells me is that it has to be somewhere in this range, right? Because this is negative pi over 2 to pi over 2. So what we just found is that we found that this is negative 75.8 degrees. So I'm starting at 0 and I'm going down 75.8 degrees, right? So this is the answer we just got. This point right here is 75.8 degrees, negative 75.8 degrees, okay? So that would be my answer if we were starting off with tangent, but we're not, right? We have to be careful because our we started off with cotangent inverse. So I want to just write over here, if we're talking about cotangent inverse output values, we already discussed, right? Those are between 0 and pi, right? Or from 0 to 180 degrees. So cotangent has to be in here, right? From 0 to 180 degrees for our possible output values, okay? 0 to pi. So what I need to figure out is if this is the answer that I got for my tangent inverse, how does that relate to my cotangent inverse problem? Okay, so for my cotangent inverse problem, I would need my answer to fall in quadrant 1 or quadrant 2, right? And right now it's falling in quadrant 4. So what we can do is we can use this idea that if we have the same reference angle, right, then we have the same tangent value. So what I can do is I can use the same reference angle as this degree angle, but reflect it across. Like if I draw this just straight out like this, right? Do you agree the distance from here to here is 75.8 degrees? That's the angle measure. So if I continue this line on out, then this angle measure would also be 75.8 degrees, away from 180, right? So these two have the same measure, which means that they would have the same tangent value. Okay, so the reason that I reflected it over here is so that I can figure out what this angle measure is, because I need my answer to fall in one of these two quadrants. So by just extending it on out and finding the reference triangle with the same measure, I know that this angle is going to have the same tangent value. So I can find this angle as being an angle that falls into quadrant 2. So all I have to do is figure out, okay, well, from 0 to 180, what is that measure, right? What is that measure that is equivalent to a tangent negative 78 or 75.8? So all I have to do is think, okay, well, this, if I went all the way, that would be 180 degrees. So I'm going to take 180 degrees and I'm going to subtract 75.8 degrees from it. And what that leaves me with is 104.2 degrees. So that is my answer for this problem. Okay, so this one was a little tricky because since we don't have an inverse cotangent button on our calculator, we had to rewrite it in terms of tangent, which is totally fine to do. But when we rewrite it in terms of tangent, we then have to think about where our possible angles, where our output values have changed going from tangent to cotangent. So the answer we get for tangent, we just simply need to find a corresponding reference angle, right, that would have the same tangent value within the quadrants that are allowed as output values for our cotangent function. Here it had to lie in 1 or 2 to be between 0 and 180. So we went ahead and found a reference triangle with the same measure in quadrant 2. And then all we had to do is calculate what is the measure of that angle in quadrant 2. Okay. All right, last one. Hang in there. Last one. All right, this one's way nicer. Way nicer. I saved a nice one for last. Okay. This one is secant. Secant value, okay? So for secant, we can just take the regular secant, right, to get rid of secant inverse. So we're going to say secant y is equal to secant of secant inverse evaluated at -4. So my secant and my secant inverse cancel out. So I have secant y is equal to -4. Right? And then we, let's check our values, right? So we're talking about secant. Secant here can be anything between 0 and pi. It just can't be pi over 2. So 0 to pi, but not pi over 2. So I'm going to go ahead and say secant inverse can be anything from, what did I just say? 0 to pi, right? But not pi over 2. So it cannot equal 90 degrees. So don't use that one. Nope. Okay. But anything else in here is our allowable measures. Okay. All right. So let's go ahead. Now we don't have a secant button on our calculator, right? We only have sine, cosine, and tangent and their inverses. So we need to go ahead and change this into something we're familiar with, which secant is related to cosine. So I'm going to go ahead and say this is the same thing as saying cosine y equals its reciprocal, which would be -1/4, right? And now we can take the cosine inverse of both sides. So cosine inverse of cosine y is equal to cosine inverse of -1/4. So those cancel, and we get y is equal to cosine inverse of -1/4. Okay. So we go ahead and notice this one did not say find degrees, right? Part A wanted us to find degrees. This one didn't say anything. So we're assuming it's in radian measures. Okay. So we're going to go ahead and plug this into our calculator. And what we get is 1.82347 blah, 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 right? And then this was in cosine. So we need to make sure that this is an okay answer. So if we look at cosine, cosine also goes from 0 to pi, right? We have no issue. It has the same range. cosine inverse also goes from 0 to 180. So the fact that we got this, as long as this is not equal to pi over 2, which it's not, right? This is not the radian measure for pi over 2, then our answer is okay. So I'm going to go ahead and just say y is approximately 1.8 radians. Okay. All right. I think we're going to stop there. 6.1 is a large section with a lot of stuff to think about, and 6.1a tends to be a little bit longer just because we have to go through the process of deriving those new graphs and finding their range values. So we're going to stop here. You should now be able to complete the assignment on my math lab. There's no worksheet for this section, and then we'll come back in 6.1b and talk about some other things. Okay? If you have any questions, let me know. Otherwise,